Hello dear students, welcome back to the lecture series on topology second with course code MTH802. Today we are going to discuss very important theorem, the Stone-Cech compactification theorem. So before stating this theorem, I would like to recall Urizen's lemma. So as you have seen in Urizen's lemma that every normal space which is also second countable, it can be embedded in a matrix space. So as in Urizen's embedding theorem, you have seen that as in Urizen's embedding theorem, we showed that that if a normal space X is second countable, if a normal space X is also second countable, then it can be embedded in in a matrix space, a very important matrix space, or in this we have discussed in one of the previous lecture, Urizen's embedding theorem. Now in this lecture we now develop similar embedding theorem for completely regular space. So in this lecture we develop a similar theorem for completely regular space, for completely regular space. Okay, so we try to develop such theorem for completely regular, a similar theorem for a completely regular space. Okay, so page number 1. Page number 2. So let's first discuss the following. If X is a topological space, if X is a topological space, and it is a subspace of some compact Hausdorff space, and is a subspace of some compact Hausdorff space Y. Let's say this X is subspace of Y, where Y is compact Hausdorff space. Since compact Hausdorff spaces are completely regular, since that Y is completely regular, so therefore X is completely regular. X is completely regular, and this X is subset of X closure, where X closure is always subset of Y. Now this Y is compact Hausdorff space, so X closure is also a compact Hausdorff space. So that means this X closure is compact Hausdorff space. Hausdorff is a compact Hausdorff space. So therefore X is dense in X, and X is dense in X, and X is dense in X, and X is dense in exclusion, because closure of X is exclusion. It's dense in exclusion. So that means this space X is dense in some compact Hausdorff. Now what we are going to prove actually in our theorem. So what's we have in this lecture, it's given that x is a, now we are going to put the following theorem. X is a, so in this section we are going to prove, we show that in this section we show that any completely regular space, that X any completely regular space, show that any completely regular space can be embedded as a dense subspace, as a dense subspace in a spatial compact horizontal space, in a spatial compact horizontal space, spatial compact horizontal space denoted by beta x, and this beta, so that's what we are going to prove. So we have a given completely regular space X, and we show that this completely regular space can be embedded as a dense subspace. That means this X closure is equal to beta x. Every completely regular space can be embedded as a dense subspace of some particular space, which is a compact horizontal space denoted by beta x, such that this beta x has the following remarkable properties, and this beta x has the following remarkable properties. What's the first property? The first property is every bounded, it's the following remarkable property, not properties. So what's that property? Every bounded continuous real function means real valued function, okay? Every bounded continuous real function on X, it's a function on X, it can be extended, has a unique extension, it can be extended, or it has a unique extension to a bounded continuous real function, which is defined on beta x, Let's see. So this is the property of beta x. If we have a given continuous real valued and bounded function on X, then that continuous real valued bounded continuous can be extended to on this beta x, where that extension is also a continuous and bounded real valued function. Before proving this, before stating that Stone-Cech compactification theorem, I would like to state the following facts. What's fact number one is that we are going to use in this theorem. It's if X is a completely regular space, if X is a completely regular space, then the weak topology generated by CXR Generated by CXR means it's the weakest topology which makes each function which is in this space continuous. That is generated by CXR. This weak topology, it should coincide with the given topology or equals the given topology, because X is already a given topology, equals the given. That's a fact 1 which we are going to use, and this fact, this is an exercise for you. You can do it easily. So the topology generated by CXR, because CXR is a collection of the functions, the topology generated by those functions is same as the given topology. It's already an X, such that this CXR with respect to that topology, CXR is the collection of continuous functions. And the fact 2 which we are going to use, it is fact 2. Second fact. Second fact. So it's if X is a completely regular space, again it's not for completely regular space, it's the relative topology, the relative topology on a subspace on a, this is a very simple, on a subspace of a product space of a product space equals the weak topology equals the weak topology generated by the restrictions of the projections of that subspace, Okay, so what its fact states precisely: suppose we have product space, okay, product topological space Xi, and Y is a subspace of Xi, and we know that what the topology on Xi, it's the weakest topology that makes each projection continuous. What are the projections? Projections are the mappings from the product space Xi to Xi. So the smallest topology making each projection continuous is the topology on that product space. And Y is a subspace of this. Then Y has a related topology with respect to this product topological space. But that related topology is same as the topology generated by the restrictions of the, because this Y is actually, it's actually product Yi, where each Yi is subset of Xi. So now we can restrict these PIs on that product Yi. So these PIs, they are the functions of product Yi to Yi. So the topology generated by these projections, which are actually the restrictions of these projections on that product subspace, is same as the related topology. This treated as a subspace of that topological space, then it has a related topology. It is a subspace with respect to the related topology, but that related topology is same as the topology generated by the restrictions of the projections on that subset, on that subspace. Okay, so these two topologies are same. Now we state our theorem, that's Stone-Cech compactification theorem. Let's write the statement of that theorem. What's the statement? Statement is let X be a completely regular space. Let X be a completely regular space. Let X be a completely regular space. Then there exists a compact then there exists a compact Hausdorff space which we will denote by beta x. Then there exists a compact Hausdorff space beta x with the following properties. X is a given completely regular space. Then we need to show that there exists a compact Hausdorff space denoted to a beta x with the following properties. The first property is X is dense subspace of beta x. X is dense. It's a dense subspace of beta x, that is x closure is equal to beta x. And the second property is every bounded continuous real function bounded continuous real function on x has a unique extension, to a bounded continuous to a bounded continuous real function on beta x. So these are the two properties which we need to verify, that x is dense subspace of beta x, where beta x is a compact Hausdorff space that we have to construct here such that x closure is equal to beta x. This is dense subspace beta x. And the second property that we have to verify, it is every bounded continuous real valued function on x has a unique extension to a bounded real valued continuous function on beta x. So these two properties which we have to verify. Let's prove this theorem. Proof is not too difficult. It's very simple. So we assume that this x is assume x is a completely regular space. Assume x a completely regular space. So assume that x is a completely regular topological space. X a completely regular topological space. Now let C of XR, let C of XR denotes the set of all continuous bounded functions, all continuous bounded functions on X. Now we use the indexed set. Let the function is in CXR. Let the function is in CXR be indexed by a set I. That is CXR is equal to these functions fi, where this I belongs to I. So indexed by this set CXR. And let's assume that since fi is a real valued function, let's assume that I is the smallest closed interval. Containing the range of fi. Let I be the smallest closed interval containing the range of fi. Then II is compact Hausdorff space. It is simple. II is compact. It is also Hausdorff space. And then II is a compact Hausdorff space. Therefore, their product is also compact Hausdorff space. Therefore, which I denote by P. P is the product II. I is in I. Therefore, this is a compact. Because product of compact space is compact and product of Hausdorff spaces is Hausdorff space. So it's a compact Hausdorff space. It's a compact Hausdorff space. It's a compact Hausdorff space. We next define a function f into this product space. Now define f from x to p by f of x is equal to fix where I is in I, because fix belongs to I, so it's a function from x to pi where the ith coordinate of this product space of this element is fix. Okay,